Principles of Operating Systems, Chapter 5, Policies for Processor Time. Most modern computing systems have several processors, but operating systems almost always have more jobs or processes to work on than it has processors available. And so there are going to be processes waiting to use the processor. And of course, there has to be some kind of a policy for choosing processes when a new processor comes available for another process. There are a number of different policies that have been used, and the one that gets used in a given system is going to depend on what the system is going to be used for. Policies on a personal computer are certainly going to be very, very different from those on time-sharing systems, and are going to be quite again different from those used for a supercomputer. There are generally two classes of processor selection types: preemptive and non-preemptive. Non-preemptive systems, once a process starts executing, once it's assigned to a processor, it keeps executing, keeps using the processor until that process relinquishes control. It might be relinquished for several reasons. It might just be done. It might encounter an input-output operation. Once the process relinquishes control, then the operating system selects another process and assigns the processor to that. In a preemptive system, processes are given access for a maximum period of time, a time slice or a quantum. Process might relinquish control before that time slice ends, but if it doesn't, it's going to be interrupted, and another process then gets to use the processor. Very few modern systems are non-preemptive. Almost all of them are preemptive. Some systems can be designed to prioritize throughput, the number of jobs that it's going to actually complete, response times, shortest time waiting for the system to respond to a process, efficiency of CPU utilization, maximizing the proportion of time that processors are actually executing process code. Now, CPU utilization should never be 100%, because if it's using 100% of the CPU, it's likely to be slow to respond to system events. Could also prioritize job fairness, trying to give each process, each job, the same amount of time. System capacity, maximizing the number of simultaneous processes, simultaneous users that the system supports. Can also have other priorities as well. The priorities emphasized on any given system will be different from one system to another and depend largely on what the computing system is used for. Most of the systems are going to be a combination of some of these. and, of course, also be designed to try to avoid deadlocks and starvation. Emphasizing any one of these too much is likely to create problems. A system prioritizing throughput is going to give higher priorities to short jobs and use long time slices that would avoid the overhead involved switching from process to process. It does create the danger of having longer jobs suffering starvation. Minimizing response time in a system would be implemented using I/O-bound processes and short time slices, maximizing the number of processes that get the opportunity to work toward the point where they need some input-output. In this kind of a system, compute-bound processes are likely to suffer. Maximizing CPU efficiency is implemented using long time slices and giving higher priority to compute-bound processes. This would reduce the frequency of switching from process to process. In a situation like this, response time is likely to suffer. I/O-bound processes might suffer starvation. A system prioritizing fairness would use a simple first in, first out waiting queue, would not assign any special priorities to any of the processes. If a system is busy and has lots of compute-bound processes, a system like this would probably end up with poor response time. A system prioritizing capacity would prioritize small processes and I/O-bound processes. Small processes occupy less RAM, and so you can put more of this kind of processes into memory at once. I/O-bound processes spend much of their time in a paused state, so they don't put any particular burden on processors while they're paused. In this kind of a system, larger processes, compute-bound processes, might very well suffer starvation. There are quite a number of algorithms that have been developed for processor allocation. First come, first served, earliest deadline first, shortest job next, highest response ratio next, shortest remaining time, round robin, priority scheduling, fixed priority preemptive scheduling, completely fair scheduler, among many others. The first come, first served algorithm is the simplest one. It just puts the processes as they come available to execute into a queue. Usually this shows up on non-preemptive systems. Once a process has the CPU, it just runs until it stops. It's the simplest algorithm. Overhead is minimal, and there's never going to be any starvation because, as that is assuming that all of the processes eventually terminate. Since it's only found on non-preemptive systems, it's only available for batch processing, only used in batch processing systems, and so it's only shows in the earliest of the operating systems. EDF, earliest deadline first processes. This algorithm places process into a queue that's ordered according to the deadlines for completion. This is, of course, a form of priority scheduling. It's assigning processes priorities. It's not a widely used algorithm, at least not in a pure form, since, at least in part, it's problematic. What do they do with a process when the system becomes overloaded, when a process cannot be completed before its deadline? The system does have a built-in aging effect. The closer a process gets to its deadline, the higher its priority. So, as long as you don't overload the system, starvation simply isn't going to happen. With SJN, shortest job next, waiting processes are kept in a queue that's ordered by the time required to complete execution. When a processor becomes available, the process with the shortest remaining execution time is chosen. This is a non-preemptive algorithm. The shortest job keeps the processor until it finishes or self-interrupts. A preemptive version, SRT, which we'll be discussing later, exists. The shortest job next is relatively simple. It does, of course, require an estimate of time required for execution. It tends to maximize throughput, tends to minimize the average response time, the average amount of time processes have to wait. Individual processes might end up waiting considerable time. Most, however, would not. It does, however, have the potential for starvation. If a system has lots of short processes frequently added, then longer processes might continually be crowded out and never get a chance to run. It's only suitable for batch systems since it's non-preemptive, and it's generally requires an estimate of execution time, and estimates on execution times would not be available for interactive processes. Highest response ratio next, HRRN, is a form of priority scheduling designed to implement aging. It's a non-preemptive discipline developed by Brinch Hansen, modifying SJN to mitigate process starvation, reduce the danger of starvation. With HRRN, the next job is not the shortened estimated runtime, but a highest response ratio. Time waiting plus estimated runtime divided by estimated runtime. The idea is that if a job has been waiting for a while, its priority gets boosted up to where even long jobs can compete for the use of the processor. Jobs that have spent a long time waiting can compete against those estimated their short time run times. The long process has a increasing priority, it does not start with a high priority, but it increases as time passes. Not as fast as the priority increases for shorter processes, but it increases. Short processes have an advantage, but eventually the longer process, if it waits long enough, will get a high priority and get assigned a processor. Shortest remaining time is an algorithm similar to SJF, shortest job first. With this SRT strategy, the scheduler puts the processes in the queue in order of the least remaining processing time. Of course, this requires an estimate of the time required for the process to complete. If a shorter process arrives while another longer process is being executed, the system will interrupt the running process, recompute its time to complete, taking into consideration how long it's been running, and puts it into the waiting queue. Of course, this involves more system overhead. The scheduler has to put processes into the queue in specific places, not just at the end. That involves more overhead. It's designed, the idea is to produce maximum throughput, and it works in most scenarios, but with the increased overhead can result in slower performance than shortest job first. Since the waiting time and the response time both increase as the process computational requirements increase. Turnaround time is based on the waiting time plus processing time, so longer processes are particularly affected. Starvation is a distinct possibility for longest processes, especially if it's a system where many small processes show up. Another frequently used, commonly used algorithm is the round-robin algorithm. Round-robin is a preemptive scheduling system. A process is assigned to the processor for a fixed time slice. If it terminates, then it terminates, and the next process from the ready queue is assigned to the processor. if it times out, it goes into the queue to be cycled through again. If it hits an I/O interrupt, it is interrupted until the I/O finishes, and then it goes back into the ready queue. If it tends to involve quite a bit of overhead, especially if the time slices are quite short and the processes get interrupted frequently. In practice, its throughput comes between that of first come, first served and shortest job first. Shorter jobs get done faster than first come, first served, and longer processes get completed faster than in shortest job first. Generally, it has pretty good response time. The waiting times tend to depend on how many processes there are, not at how long the other processes are. Starvation doesn't occur since no priorities are given. They go into the ready queue, and when their turn comes, they get processed. With priority scheduling, you're dealing with a non-preemptive system. It's one of the most common systems used for batch processing. The idea is to give preferential treatment to some of the jobs and lower priority to the other less important ones. We've seen examples of PS, priority scheduling, shortest job first, and HRRN are examples of priority scheduling. Programs with highest priorities are processed first and not interrupted. They're allowed to complete or to interrupt themselves for I/O or other reasons. Priorities are assigned based on many different characteristics depending on the system. Who the user is, how much memory is required, what peripheral devices are required, how long it's going to take to run the job, how long it has been waiting, that's called aging, and many others. Fixed point preemptive scheduling, FPPS, is commonly used in real-time interactive systems. With this system, the scheduler ensures that the processor will be assigned the highest priority task of all the ones currently ready to execute. Processes are given fixed time slices, quantums, and when the process finishes, self-interrupts for I/O or ends its time slice, the scheduler once again identifies the highest priority list from the ones ready to execute. It has the advantage of making sure that no task uses the processor for long time periods, longer than that of a quantum, a time slice. It is, however, vulnerable to process lockout, thread lockout, since priority is given to higher priority tasks. The lower priority task could wait for indefinite amounts of time. One common way to avoid the problems associated is by aging, gradually incrementing the priority of waiting processes, waiting threads, ensuring that eventually they will get the opportunity to execute. The Completely Fair Scheduler, CFS, is a process scheduler that was built into Linux starting in 2007. It deals with CPU allocation for executing processes, and it aims to maximize overall utilization and also optimizing interactive performance. Like the older scheduler, it uses a concept called sleeper fairness, which considers sleeping or waiting tasks as well as running tasks in establishing priorities. That means that your interactive tasks, which spend most of the time waiting, get a better share of the CPU time when they need it. When processes can be divided into different categories, then system can separate them into different queues with different algorithms for the different queues. Of course, this is only if you can separate them into different groups. One example, you can separate them into foreground interactive and background batch. They have different response time requirements and have different scheduling needs. Another common subdivision is I/O bound versus compute bound. With multiple level queues, scheduling has to be done or can be done between queues. Scheduling processes from different queues. Different common options are strict priority, no job in a lower priority runs until all the higher priority queues. Round robin, each queue gets a turn to provide a process to be executed. Some systems have different time slice lengths for processes from different queues. With this algorithm, it's assumed that jobs don't move from one queue to another. Once they're assigned to one queue, that's the one they're in until they run and finish. Multi-level feedback queue scheduling is similar to ordinary multi-level queue scheduling, except that with feedback queue scheduling, you can move jobs from one queue to another. There are several reasons you might want to do this. The characteristics of a job can change from CPU intensive to I/O intensive during the course of the execution. And so it might be appropriate to switch a job from a CPU intensive queue to a I/O intensive queue. Aging can be incorporated, moving a job that's waited for a long time from a lower priority queue to a higher priority queue. Multi-level feedback queue is much more flexible because you can tune it to work for different situations, but it's also much more complex to implement and so more time intensive. Multi-level feedback queue scheduling is more complex to implement because it has a number of parameters that will have to be adjusted. Some of those parameters that's likely to be involved would be how many queues there are in the system, what the scheduling algorithm is for each queue. They can be different from one queue to another. how you go about upgrading or demoting a process, moving a process from one queue to another. And it might be different from different queues. And how do you determine which queue to enter a process in when it enters the system to be in the beginning? When you're designing an algorithm in a multiprocessor system, there's another problem that the algorithm has to take into consideration: identifying a processor to assign to a given process. Should there be some preference in the assignment of processors, or should it simply be first come, first served? One of the things that complicates this decision is cache memory. Individual processors have their own cache memory, and this is faster than other cache memory. Use of the cache associated with the specific processor can really speed up accesses to these memory locations. If a process switches from processor to processor each time it gets access to execute, then the data for that process has to be copied, reloaded from main memory into the cache for the processor selected. And that tends to reduce the effectiveness of using cache, since the idea is to avoid using relatively slow main memory. Usually, systems attempt to assign the same processes to the same processors. This is called processor affinity. Comes in two flavors: soft affinity, when the system attempts to keep processors working on the same processors, but no guarantees. Hard affinity, on the other hand, is a system where the process specifies that it be assigned the same processor each time. Linux, among others, supports hard affinity. Main memory architecture can affect process affinity too. If some CPUs have faster access to some regions of memory on the same board, and others have better access to other regions of memory, if we have non-uniform memory access, then clearly you should have the process, all of a process, loaded into memory that is fast for the processor working on the process. Virtualization gives another layer of complexity for processor scheduling. With virtualization, typically you have a host operating system operating on the real processor or processors in the system, but you have virtual processors created and guest operating systems installed to execute by these virtual processes. The host operating system then creates virtual processors and loads operating systems for them to use. the operating system then are executed by virtual processors just the same as if they were a real processor. The guest operating systems then, of course, don't have any reason to operate as if they were anything but real processors. They make all of their scheduling assumptions, assuming that the processors they're executing on are physical, real processors, CPUs, and interactive and real-time performance can be severely compromised working on a guest system, since there will be interruptions that they won't recognize taking place, let alone make decisions assuming they might happen.